Students, can you hear me now?
Yes, ma'am.
Am I audible? Can you just let me know? Students, can you hear me? Okay, fine. Thank you. Oh, this time I'm muted and I'm speaking. Okay, thank you so much, Chris. Yes. So I was discussing about ozone. A minute. Huh. Yeah. I was discussing about ozone and I'll continue my discussion. Fine. Here, the most important thing is the different oxy acids of sulfur. Okay. What is important is the different oxy acids of sulfur. Let's continue. So you have, tell me which is the most stable allotrope of sulfur. Name all the allotropes. Tell me which is the most stable one. You can just unmute and speak. Why take the pains of so much of? Okay, rhombic is the most stable one. Okay, very good. So let's talk about the crystalline allotropes of sulfur. You have the rhombic sulfur or the alpha sulfur, monoclinic sulfur or the beta sulfur. You also have the gamma sulfur, which will be called as like plastic sulfur or milk of sulfur. Yes. Rhombic sulfur is the most stable form and it's stable below 95.6 degrees centigrade. What you told in Kelvin ion centigrade. 95.6 degrees centigrade. Below that temperature, it's very, very stable. Above that, when you heat it above that, it converts into the monoclinic form. Fine. We'll right now quickly discuss these things. Both are equally stable at 3. Okay. Definitely. 95.6 degrees is a transition temperature. See, I'll make it simple. Transition means change. So at that particular temperature, you will that's the barrier. That's the like what? Like a like 0 degrees a barrier above which the ice starts melting into liquid and below 0 degree, you'll know it is solidified. Exactly. In that way, Faizan, you're absolutely correct. So that's a transition temperature. Above that temperature, it remains in the beta form. Below the temperature, beta form is same as monoclinic form. Below the temperature, it remains in the rhombic form. Fine. Thank you so much. And I would like to definitely discuss certain questions with you people, but let's first complete these. The P block at least. Yes. Rhombic sulfur. Or on the second session, maybe I can ask you a few more stuffs. So you have rhombic sulfur, mono. I love the monoclinic one. And this is plastic sulfur or amorphous no powder. These two are the crystalline forms. I like this better. Yes, and thermodynamically, rhombic sulfur is more stable. Sulfur, sulfur linkages. So, will be nonpolar, would be soluble in nonpolar solvents like carbon disulfide, but will be insoluble in polar solvents like water. S8 units, puckered crown shaped structure. This is your S8 units. Both the monoclinic and the rhombic form exist in this crown shaped structure. I would like to know the hybridization of sulfur in S8. I would like to know the hybridization of sulfur in S8. Give me 1 minute. Little cough. Yes. Thank you so much. Very good. 3, 4, 5. Wait, I'll draw it in this way. 1, 2, 3, 4, 5, 6, 7, and 8. Yes. On a particular sulfur, you can see 2 bond pairs and 2 lone pairs. sp3. So many answers. Students, just feel free to converse, discuss things with me. Have doubts in any other topics? Feel free to contact me or sir, either one. We both will help you out. Fine. Right now, a little busy, so you can just get in touch with me. So both are puckered or crown shaped S8 units are there. S2 is paramagnetic. Students, how do I justify S2 is paramagnetic? Yes, sp3 is perfectly correct. 2 bond pair, 2 lone pair, bend geometry. S6, 6, you think of that cyclohexane, it will be existing in the chair shaped form. This one justified, this one justified. It exists in the wafer form at high temperature, that also understood. S2 is paramagnetic in nature. What do you mean by that? And how do you justify its paramagnetic? O2 is paramagnetic, MOT. And similarly, if I just apply the same logic, because oxygen and sulfur both have valence electrons same in number, right? So in similar way, I can justify S2 to be paramagnetic. Okay, very good, Shifali. Even I thought the same thing. Students, it's like a discussion going on. If any other better ideas, please share. You may have a better one than mine. Yes, even I thought O2 paramagnetic due to MOT. S2 also. We may not draw so many because we just don't draw it. But if you apply the same logic, you find S2 also to be paramagnetic in nature. Fine. That's the valid reason. Okay. Sulfur dioxide. Preparation. Burn sulfur in the presence of air or oxygen. SO2 is a very powerful pollutant. Pollutant. When dissolves in rainwater, basically SO2 is less stable than SO3. So basically, after when it's exposed to air or atmosphere for some time, it gets basically oxidized to the more stable SO3. And when SO3 dissolves in water, H2SO4, H2SO4 is a very important troubling component of this rain, and we call it acid rain. Yes. So by burning of sulfur in the presence of oxygen. The lab method includes take some sulfides, you can take some bisulfides also. And when it reacts with dilute acids like HCl, SO2 is liberated. Students, can anyone tell me how to detect the presence of SO2? Think of redox chapter. SO2, like CO2, your lime water turns milky, and when you pass excess of CO2, the milkiness disappears. Some idea if you give me there? If you give me here also, I mean. Students, when you bring a filter paper dipped in acidified K2Cr2O7 solution. So I have acidified K2Cr2O7 solution means I have K2Cr2O7 to which I have added dilute H2SO4. So this solution is there. I'll dip a filter paper and expose it to SO2 coming out from some source from this reaction, suppose. Okay, Hina. Yes, similar thing where I'm telling. So the orange color of this potassium dichromate solution in acidic medium turns. Anyone? Anyone? I'm waiting. Pass the gas through acidified K2Cr2O7 solution. Orange turns green, green, green. Green is the answer here. Good. Because Cr plus 6 gets converted into Cr plus 3 state. Fine. I'll try my best to give you all the additional inputs. You can correlate it with other chapters. At the same time, we can cover things of this chapter also. Fine. Similarly, bisulfides also give SO2 with dilute HCl. Disulfide sulfides they will liberate SO2. Sulfur dioxide. It's a colorless gas with a pungent odor. Heavier than, if you look into its vapor density, it's heavier than air. It's why is it highly soluble in water? If you remember, because we discussed about group 14 also in our recent discussions, CO2 is only slightly soluble in water under ordinary pressure. You increase the pressure, apply Henry's law, and then solubility of CO2 increases. Very good. Whatever I ask. Polar nature, like dissolves, like water is also polar covalent. SO2 is also polar covalent. That's the reason. Perfect. Okay. Of course, it's an acidic oxide. Oxides of nonmetals are acidic in nature. There are a few oxides of metals which dissolve in water to give an acid. Metal oxides which are also acidic in nature, something I said. There's certain metal oxides which are generally metal oxides are basic in nature. Transition, no, not CaO. CaO is basic oxide. CaO is basic oxide. There's certain oxides of group block, D block. Certain oxides of D block like manganese, I can recollect manganese, vanadium, chromium, they will dissolve in water to produce acids. Yes, yes, yes. Chats, yes, yes. So this one is acidic oxide. It dissolves in water immediately. Don't give it chance to get oxidized to SO3 because when SO3 is produced, it will produce H2SO4 on dissolving in water. But if you directly add water to SO2, it produces sulfurous acid. Students, the N factor of sulfurous acid first. What number line she draws? Sulfur minus 2, it can gain 2 more and form minus 2. Or it can attain minus 2 oxidation state like H2S. It can lose all the 6 electrons and attain plus 6 oxidation state. So it can either gain 2 electrons and attain minus 2 oxidation state. It can lose 6 electrons, sulfur. This is the number line for sulfur. Right now, SO2. We'll write SO2 up in minus plus 4 here. Plus 4. Yes, Atika, you have answered it correctly. Vaidehi Shri. Okay. I didn't, I'll be honest, with so many things and I forgot. I'll I'll find it out. TeO2 I never bothered to and I forgot also. But we have one more session. So after the lunch break, I when you people are telling it is amphoteric, it will be amphoteric. I was thinking it to be basic oxide, but yes, I didn't check some source. I'll do that. Yes. No, Nandana, N factor is not one. Sulfurous acid is this way. Sure. Thank you for reminding me. H2S H2S 1 2 3 4. Oh no. This one though I drew sulfuric acid. Sulfurous acid. How do I draw sulfurous acid? Who's going to help me? N factor is 2. Here only decided. There are two hydrogens and both are bonded to H2SO3 over. Everyone N factor 2. Fine. This is sulfurous acid. I'm very much bothered here to ensure that I discuss all the structures of oxyacids of sulfur important. Student sulfuric also I'll draw. It's an easy one. Everyone understood? This is H2SO3. H2SO3. Sulfur can expand its octet, not problem. 1, 2, 3, 4, 5, 6, 7, 8. 8 is also there. It can expand its octet, not a problem. In either cases, the hydrogens are directly bonded to highly electronegative oxygen atom. Fine, everyone understood? Yeah, I wanted to ask
Yes.
one thing. What is H2SO2? Any idea? Hi, there has been, like, there's a saying, you open your mouth to ask anything. You're 100% sure some or the other student will give you the answer. Yes, it is hyposulfurous acid. Hypoacid, yes. So many people answering. I'm so happy. Students, one more thing here. So now this n equal to 2 means, let me write it more clearly because it will be there in your notes. No, I'll just write it as basicity. Comment on the oxidation state of sulfur here. So the basicity is 2. Here also, both the hydrogens are directly attached to highly electronegative oxygen. So the basicity is here also 2. Oxidation number of sulfur here is plus 4. Here it's plus 6. Here plus 2. Convinced? And the basicity? Here this part extends here. I hope nothing else is written here. Okay, fine. Again 2. Yes, just have a look. Any other confusion, any other doubt? You reminded me well and good. And good, there's one more session also. So while I'll be having my lunch, the break, I'll just once find out. We should know once from some sources. Okay. So colorless gas with a pungent odor. It's polar, so soluble in highly soluble in water. Its vapor density is greater than that of air. Acidic oxide, non-metals generally form acidic oxides, except those exceptions we just now discussed. So it will dissolve in water to form sulfurous acid. Now, as I was discussing this in the previous session also, and sulfur is in the plus 4 state. It can lose electrons and act as a reducing agent because when it loses its electron, it itself gets oxidized. So when something gets oxidized, it acts as the reducing agent. Both, very good. Both. So, but more commonly, though it can act as both, which role does it play more? You need that also for the examination like viewpoint. So here it gains and acts as an oxidizing agent. I have seen more of reactions, and I'm pretty sure here it mostly acts as an reducing agent. Why? What happens? No, see, plus 6 is a very stable state. Now think students in this way: non-metals, non-metallic oxides or non-metals will be very stable or will be very happy in high oxidation state, because greater the oxidation state, greater will be the acidic nature of that non-metal. Non-metals like acids or acidic nature, I mean. Non-metals love acidic nature. So sulfur here would be happy to go to the plus 6 state. So if it goes into its plus 6 state, it's more acidic now. And and non-metals being more acidic is good thing. Metals should be more basic, non-metals should be more acidic. So it can go for both reactions of SO2 as an reducing agent is very relevant or very important. Everyone, because it will conveniently go from plus 4 to plus 6. Plus 6 is very stable, so it gets oxidized very easily, so it acts as a reducing agent. Lots of reactions are there, uh, and important from the examination viewpoint also. Both are there. Don't misunderstand that she told only reducing nature. I said both, and it can act as both, and there will be a lot of reactions of both. I've seen. I'm talking, and we don't have other time for a lot of other things, right? Focus is exam, neat. So mostly questions come showing SO2's reducing nature. It can act as both. Questions can come on oxidizing nature also, but mostly questions will come showing its behavior as per my experience and what I've seen past years, like that. So just trying to give you the hint that at least, or the reducing nature, or its reactions where it behaves as a reducing agent, at least you do in a proper way, at least. So when it gets reduced, it moves from plus 4 to the 0 state. When it gets oxidized, it moves from the plus 4 to the plus 6 state. So SO2 plus orange dichromate, just now we saw it converts into green Cr3 plus. That shows its reducing nature. Someone was studying this. Sorry, that time I didn't tell. So many things are there in the chats, and I'm really sorry. I missed. Now I remember someone told that purple becomes colorless. That's also a test for SO2. Absolutely correct. And both the reactions show its reducing nature, and such questions can be asked. Wait, I'll also ask you one redox question. It can also reduce Fe3 plus into the plus 2 state. That also illustrates its reducing nature. This color changes. Its behavior as a reducing agent is important. It can also act as an oxidizing agent by itself getting reduced to sulfur. Means from plus 4, it goes to the 0 state. It gains electrons and hence acts as an oxidizing agent and oxidizes H2S to S, I minus to I2, Br minus to reddish brown bromine. Fine. Now, if you give me permission to ask you one question, how many moles of KMNO4 in acidic medium is required to oxidize 1 mole of, this would be better, how many moles of KMNO4 is required to oxidize 1 mole of SO2 in, should I discuss this immediately, or should I give you some time? Are you people solving or wondering why did she give this question now? Just let me know. Mute, like unmute and speak. Students finding any difficulty with my way, means am I going too fast or anything? You can always let me know. Any difficulty because suddenly adapting to my ways, or tell me I'll adapt to your ways. Okay, please do. Okay, thank you, Vedeshi. You can please feel free to let me know because I don't know you people. So I will teach my way out. So do help me. Okay, okay, fine. I got the answer. So you can start my discussion. Time is the factor. Students can't give you a lot of time also, but at the same time, n factor of KMNO4 in acidic medium is 5. SO2 You should know that KMNO4 can only act as an oxidizing agent. So right now with KMNO4 in acidic medium, you are behaving as a reducing agent. And when we are behaving as a reducing agent and getting converted into sulfate, you're basically changing the state from +4 to +6. And what we do, it's not possible you gain 5 and lose 2 electron. So what we do is equation 1 into 2, equation 2 into 5. It's basically 2 KMNO4. I got the correct answer, no doubt. Reacts with 5 SO2 and so on. So when 5 moles of SO2 reacts with 2 moles of, students, 5 electrons are gained during the reduction of Mn +7 to +2. 2 electrons are lost when sulfur gets oxidized to +6 state. To equalize the number of electrons lost and gained, we should cross multiply. So 2MnO4 minus reacts with 5SO2. So 5 moles of SO2 reacts with 2 moles of KMnO4.
KMNO4.
But the question is when 1 mole of SO2 reacts, it reacts with how many moles of? I got the answer long time back. But considering each and every student, from my end, I should discuss it in detail when I've asked a question. The answer is 0.42 by 5. Everything is absolutely correct. Fine, everyone. Can we proceed then? So basically, SO2 acts as both oxidizing as well as it's not 2.5, it's 2 by 5 or zero point 0.4 moles. Fine? Okay, mistype. Absolutely fine. Okay. Oh, yes. So, so what happens is, um, ultimately we saw SO2 can act as both oxidizing as well as reducing agent. I was just trying to say that in exams I have seen more questions like this kind. This is one of the simple example where SO2 is behaving as a reducing agent, more of it asks, that's it. And personal opinion, that's it. Sulfuric acid, king of chemicals, oil of vitriol. It's an oily liquid, right? And you have to prepare it by contacts process, which involves 3 steps. The first step is burning of sulfur or sulfide ore in the presence of oxygen. Okay, sulfur burns in the presence of air or oxygen. Conversion of SO2 into SO3 in the presence of vanadium pentoxide as the catalyst. This is an exothermic reaction. Tell me the forward reaction will be favored under what conditions? Help me out. So it's an exothermic reaction. The forward reaction will be favored at low temperature. Agreed. And if the if you increase pressure, reaction should move in a direction where the gaseous moles are less, which again means forward direction. High temperature, low pressure. Oh, before that only everyone has typed. Anyone else, if you think that X and Y are answering because they know and I don't know, you have to let me know. There are two things. One is if I tell something which you already know, you will be irritated. At the same time, if I say something and you don't know and you're not letting me know, you can at least type. I'll not read out your name. But please explain this again in detail or in detail. One word detail, I'll understand. Yes, students. Otherwise, if you understand, it's low temperature and high pressure, which favors the forward reaction here, forward direction here. Yes. Give me a minute. Yes. Now, SO3 is first absorbed in H2SO4 to prepare oleum. We just don't add directly water to it. You will not get H2SO4 of your desired concentration. It will not be perfect. Forward reaction. Okay. So SO3 is first dissolved in H2SO4 and SO3 dissolved in H2SO4 is known as oleum. This oleum will next be hydrolyzed. I want to draw oleum. If I go wrong, you have to help me. Okay, how do I draw oleum? The best way to draw oleum is, okay, fine, I've already drawn, so I'm not going to erase. OH, OH. So I'll draw two sulfurs and put OH, OH. Now 7. So 1, 2 gone. 3, 4, 5, 6. The strategy should be this. I to already know, so I'll be like drawing like this. Sulfurs you'll draw. H will be always attached to O, and OH will be always attached to sulfur. Always. This is true. SOH, SOH. Then 2OH, 2 O's gone. How many O's left? 5. 1, 2, 3, 4. You know, sulfur can expand its octet. 1, 2, 3, 4, 5. H2, S2, 1, 2, 3. Oleum, is it correct?
Yes, ma'am.
Oxidation number of sulfur I want, and I want basicity, everything I want. I know I want one more name also for oleum. Like you told, no, sulfurous, hyposulfurous, and sulfuric. SOS linkage, yes. Basicity 2, yes. Oxidation number, sulfuric, pyro, sulfur. I got two different answers. Okay. Pyro. Here I'm asking oxidation number. Hybridization you want? I'll add. Hybridization. sp3, do I have to agree? Pyrosulfuric acid. sp3. Plus 6. Excellent. Oxidation number, basicity, hybridization. Everything is correct. Name, pyrosulfuric. That's also correct. So many answers. Very good, very good. Keep it up, students. Yes. So now when it's diluted, you get different concentrations of sulfuric acid. And here, the percentage purity, if you consider impurities will always be there to trouble, no? Around 96 to 98% pure sulfuric acid can be obtained. Tell me one property of sulfuric acid. It's a very strong acid. Along with acid, it can act as an oxidizing agent as well as a dehydrating agent. But remember, this dehydrating agent is only concentrated H2SO4. Concentrated H2SO4 is dehydrating agent. So basically, sulfuric acid is a yellow, not yellow, I'm so sorry. Uh, tell me. When I've said the term yellow, tell me what was going on in my mind. Think of nitric acid. Think of nitric acid. That's also colorless. Why then she's telling yellow? When H2 HNO3 is kept for some time, some amount of NO2 dissolves in it by decomposition. Some HNO3 decomposes, you have some HNO3. Here it's colorless. HNO3, slip of tongue. HNO3 decomposes to form a small amount of NO2. That NO2 dissolved in HNO3 is slightly yellowish in color. Otherwise, HNO3 is also colorless, pure one. This is also colorless. Sorry. It's an oily, colorless liquid. OA stands for oxidizing agent. Yes, Paisan. Yes, you're absolutely right. Yes, it's a dehydrating agent. Students, tell me one organic reaction where we use this as a dehydrating agent. We can correlate other things also, whatever remaining days. I can help you correlate little physical, little organic, very strong acidic character. Name a reaction in organic chemistry where concentrated H2SO4 acts as a dehydrating agent. Alcohol to alkene, agreed.
Grignard.
Esterification? That was the thing in my mind because of which I asked the question. I have to agree. Yes, very good. It's a very strong acid. Hydrogen bonding will be possible? Yes. So, hydrogen bonding basically makes it less volatile. Dilute one. It is neither a dehydrating agent or an oxidizing agent. It's just an acid. So oxidizing nature of concentrated H2SO4 is very important. It acts as an oxidizing agent and gets reduced to SO2. So it just jumps from +6 to +4. So when it acts as an oxidizing agent, it should get reduced. To get reduced, it should add electrons, but this person just adds 2 electrons and produces SO2. That's the reason it is termed here as a mild oxidizing agent. A strong one it will add a few more electrons, right? So it's a mild oxidizing agent, but yes, it's an oxidizing agent and it reduces to SO2. So the metal, when it reacts with concentrated H2SO4, produces metal sulfate, SO2 and H2O. Gets oxidized to +4 state from +6 state. Dilute acid just acts as an acid. So if you take a metal, take the example of manufacture of hydrogen lab method. Take some zinc granules. Basically, you can take some impure zinc granules, zinc copper couple. You treat it with H2SO4 dilute. What will happen? Fine. This is what will happen. Very good. This kind of list or chart you need. But this normally undergoes a normal displacement reaction. Here, this is acting as an oxidizing agent. So this reaction on the top is a redox reaction. This is a non-redox, a normal displacement reaction. Copper. Hydrogen is above copper in the reactivity series. With dilute, no reaction. With concentrated, yes, because it is not acting, I'm sorry, it's not participating or taking part in a displacement reaction. Oxidizing agent. This is the reducing agent. It's taking part in a normal redox reaction. So copper can react with concentrated H2SO4 because there it participates in a redox reaction. In dilute one, it's below hydrogen in the reactivity series. Even ordinary nitrogen and carbon will not react with dilute H2SO4. But with concentrated H2SO4, nitrogen will be oxidized to its highest possible oxidation state. Same is true with carbon. So it oxidizes. It means what? Concentrated H2SO4 oxidizes carbon from 0 to +4 state, nitrogen from 0 to +5 state. Copper reacts only with concentrated H2SO4 via redox reaction. No displacement is possible because copper is below hydrogen in the reactivity series. Uses as a dehydrating agent in the esterification. Other things are there: petrol refining, fertilizer formation, drying agent, store batteries, lead storage batteries. Remember secondary batteries, secondary cells, electrochemistry, lead storage batteries. Very important. A lot of structures will come. A few I already discussed to reduce your burden. Normal acids and thioacids. Normal acids and thioacids, the differences in thioacids, there will be direct SS linkage. Sure, Vaidehi. I will tell you. Where are, let me see where slide is there, where space is there. Students, can you just give me 1/2 minute where I will just tell Vaidehi that this is boric acid. Afterwards, I'll forget. That's my problem. Boric acid. Look into boron. It is, by the way, it's not acting as a protonic acid. Protonic acid means an acid which will lose its H plus, like HCl. splitting into H plus and Cl minus. H2SO4 splitting into 2H plus and 1 sulfate. Here what happens is boron as an incomplete octet. So when it's short of 2 electrons to complete its octet, it is acting as a Lewis acid. Step number 1. Next I'll ask you clear or not, but let me complete. Lewis acid, number 1. Number 2. When it acts as a Lewis acid, we will find its N factor how? N factor for a Lewis acid will be LAL, right? Los Angeles. So N factor for a Lewis acid will be the equal to the number of electron pair it accepts. N factor for a Lewis acid will be how many electron pair it accepts. It already has 6 electrons. Its target is 8. Means it's too short of electrons to complete its octet 2. But they have not asked number, they have asked pair. Which means it just needs one pair of electrons to complete its octet. A octet is 8. It already has 6. It needs one more pair to complete its octet. So its N factor, which is also it's equal to basicity, is 1. Because it will act as an electron pair acceptor. How many electron pair will it accept? 1. So its basicity is 1. In spite of the fact that these are 3 hydrogens which are directly bonded to highly electronegative oxygen. In spite of that. Now strong or weak? It's weak. Who decides strong or weak? By looking at HCl, H2SO4 or acetic acid, is it written on their name or face? No. Experimental calculation of alpha, degree of dissociation. If it's 1 or nearly 1, it's a strong acid. If it's quite less, much less, like zero point 0.1, 0.05, etc., etc., it is regarded as a weak acid. Okay. So one last line I'll write. So what will it do? Suppose I have NaOH. It will say, okay, now I can complete my octet by via coordinate bond from OH minus to boron. Where my hybridization was sp2, now I become sp3. And now this is the way I react with the base. That's the reason it's an acid. It reacts with the base to form a salt. Can I proceed now? Thank you, others, for the patience to listen when someone is asking. Thank you so much. Vedeshri, done? Okay. SS linkage. Thio linkage means SS linkage, whether a single or a double bond. If two sulfurs are directly linked in a particular oxyacid, that's known as a thio acid. Fine. Normal acid. Normal acid will have S linked with OH or double bond O. That's a normal acid. If there's a SS direct linkage, whether single or double bond, it will be known as thio acid. Students, US is used for the generally lower oxidation state. Like if the maximum oxidation state for sulfur is +6. So for +6, it will be ic. Thionic means the higher one. The lower one, okay, yeah, +5. Chalo, +5 also. The higher one. If in thionic, only these two are possible, suppose. That also I'll check in the different structures. The higher one will be ic, the lower one will be us. These three we saw. No harm in just having a look once again. Okay. There's a lone pair here. Comment on the hybridization here, students. Here the sp3 you people told that we'll consider only the sigma bonds 1, 2, 3, 4. Pi is formed by sideways overlap of unhybridized orbital. This one, students, lone pair will consider or not consider. I'm getting two different answers. Will ammonia types will consider. Chalo, sp3 should be sp3. Very good. This is also sp3. Two lone pair, two bond pair, water types, methane types, ammonia types, water types. Fine. Basicity is 2 each because the highly electronegative oxygen bonds directly with the hydrogen. So these hydrogens have directly bonded with the highly electronegative oxygen. So it's 2 each. 2 in each case. Pyrosulfuric acid or oleum we just now discussed. Let's try with the formula H2S2O7. If I use the formula plus 2 plus 2x plus 7 into minus 2 is 0. 2x minus 12 is 0. Correct? Or wait. Plus 2 plus 2x minus 14 plus 2. Okay. Correct now?
Yes.
Yes. Plus 6 here. What about H2S2O6?
+5.
Very good. Excellent. Today I'm seeing Chris, Sapna, a few more new names who are interacting me other than the other usual names who I'm now acquainted with. Okay, fine. Oleum is basically used in the preparation of benzene sulfonic acid. Can you use oleum in the preparation of phenol also? Absolutely good. Good grasp over the topics. Okay, bad. Bad means I'm telling myself bad. Why did I click the structure? Here, in order to draw the structure, the two sulfurs are directly attached. So I've shown them. Not a problem. I was thinking of asking you people to draw or myself drawing before the click. Anyways, for the next time. So it's H2S2O6. 1, 2, 3, 4, 5, 6. H2S2O6. Oxidation number also you calculated here as plus 5. Basicity is the same here. It's 2. Good. Students, thiosulfuric acid H2S2O3. The name tells it all. When I say thio, but still you'll draw without my help. The name tells it all. Yes, Pezan, correct. Use NaOH. Yeah. So here you have a SS linkage. OH will be there. One more oxygen, no? H2S2O3, correct? Very good. When you see these people, you will use the formula to find out the oxidation number. And you will see that it's coming to be exceeding its maximum possible oxidation number. In such a case, yes, all the oxygens are not in the form of oxides. Some are in the form of peroxide. So don't trouble them. Strike it off. In the exam, you may not need to draw the structure. You know the answer will be plus 6. The same story here. You cannot exceed the maximum oxidation number. So in both cases, there are peroxy linkages for sure. It's a mixture of oxides as well as an additional peroxy linkage must be there. So both of them are peroxy acids, each sulfur in either cases having an oxidation number of plus 6. Yes, we'll have to consider the maximum oxidation state. If the oxidation state, when you go for a theoretical calculation and you get a particular oxidation state or oxidation number, and that exceeds your maximum oxidation number, which is possible for that element, like plus 5 for nitrogen because it has 5 valence electrons, or plus 6 for sulfur when it has 6 valence electrons. You strike it out and write the answer as the highest oxidation state. Yes. So oxidation states in either cases are plus 6 each. Basicity, how many replaceable hydrogens are there? Except the fact for orthoboric acid, well, for Vedeshri, we could revise it again. Yes. Per disulfuric acid. Per comes from the peroxy thing. Peroxy disulfuric acid also it's called, Marshall's acid. This one is Caro's acid. Very important. This oxy acids of sulfur. And in the previous discussion, oxy acids of phosphorus is also very, very relevant. Thiosulfuric I have just now drawn. Do you know? Acha, chalo. Not do you know. Individually, tell me the oxidation state. Central one, corner one. Sulfur's oxidation number. And next click if it shows, so I'll not. May or may not be there. I don't know. This sulfur here just behaves like an oxygen. This sulfur is sp3 hybridized, but this sulfur has two lone pairs and one bond pair, sp2 hybridized. Yes. So this sulfur is sp2 hybridized. This one is sp3 hybridized. So being more electronegative, I'll put -1 per bond, so -2. And here you check, it will finally come out to be plus 6 plus 2. Your -2 plus 2, -1 plus 1, -1 plus 1. So one sulfur in the central one is in plus 6 state. You can check. Students, what we do here is, say for example, I have a particular bond or linkage to find out the oxidation number. For the less electronegative atom, like hydrogen is slightly less electronegative than carbon, right? For per one bond, per bond, we'll put +1 for the less electronegative, -1 for the more electronegative. +1 for the less, -1 for the more. +1 for the less, -1 for the more. +1 for the less, -1 for the more electronegative element. And hence, the average oxidation number one should be plus 6 minus 2 by 2. Sorry, plus who will, okay, chalo. H2S2O5. H2S2O5. Basicity 2. Comment on the oxidation number. Chalo, comment on the average oxidation number. That will do. Okay, very good. Center side, very good. Here you can overall comment on the overall oxidation number. Very good. +4. Pyrosulfurous. Be very particular about what is pyrosulfurous. Pyrosulfuric is H2S2O7. Average +5 it is coming. 2 plus 2x plus -10, 2x minus 8 is 0, 2x is 8, x is 4. 4 is only coming. Students, correct, no? Average +4 only it's coming, right? Basicity is 2. No problem, no problem. Nandan. No, I generally ask, you must be wondering, your teacher, so many classes back to back, no? Sometimes, I did it right, no? Like that. Yes, yes, no problem. Oxy acids containing linkages, S linkages. thionous and thionic acid. I'll tell you a very easy technique here. In thionous acid, you don't have to worry about this complex thing. Don't worry, it will not come in neat. Yes, thionous acid will have this kind of linkage. S will be there. Definitely, it will be bonded to some S. That's the reason this thio is there. Thio for thio, this. If it is us, there will be only one double bond and one OH. Here also, if it is us acid. What did I say? I'll repeat once again. For thio, I will put this. This is for thio. Thio, us, thionous acid. One double bond, one OH. One double bond, one OH. So thionous acid. One double bond, one OH. No, two double bond, one OH. Two double bond, one OH. In this types, thionic. This was in general. If you add more sulfurs here, this will do. Two double bond, one OH. Very good. Two double bond, one OH. Ick. One double bond, one OH. Us. Thio SS linkage. Easy. Chalo, when we have written these two, let us write their names. H2S2O4. The first one with this is thio. We can write it on this side also. H2S2O4. This is H2S2O6. Sulfur's oxidation numbers that much. I want to sit for a while so that you do this. Tell me. First one. Very good. You're going to practice these structures. Please do that. Many of them you must be knowing. See, when you study, how really should you study? Say, suppose there are suppose 12 such structures. Some you must be already knowing. Written so many exams, you will always be knowing. Then you think, okay, it's not 12. Say sulfuric acid or sulfurous acid, I already know. I know it's only 10. Out of 10 that you categorize thio, non-thio or normal. In thio, thionous, thionic. You categorize. Then categorize a few as the peroxy linkages. H2SO5, H2S2O8. One is pyrosulfurous acid, one is pyrosulfuric acid. H2S2O5 us, H2S2O7 pyrosulfuric. Like that you categorize and when you study, it becomes easy. Fine? Followed
Yes,
the
ma'am.
same thing here. The only thing which I didn't do is it's okay, understood? This. Yes. Ik 1 plus 5, us 1 plus 3. The one which we are discussing right now. Basicity is 2 in either cases. Fine. I'll stop sharing because I'll start group 17 now. Give me a minute. So, people, what is your strategy of studying right now? What you people are also studying in organic, or in the class inorganic is going on, so you're taking up some? I'm only talking about chemistry, that's what I know. So, what do you generally do? Different people will have different strategies. Some, suppose a particular chapter is going on, simultaneously they study the same thing. Or some people ensure that, acha, this one is at least going on, she's at least revising. Okay, okay, okay. Fine. Understood. Faizan, good. So this one that she's doing simultaneously, let me do either organic or physical, or little organic and little physical. Good. And I can clearly see you people answering a lot of things. Very good. Okay, can I ask a question? Um, wait. Want to give myself a rest for a while? Okay, okay. One question right now in this class, and then we'll start, and then maybe after this I can ask you more. Fine. What is produced when iodine reacts with concentrated HNO3? Can understand it's a factual question. What to do? Inorganic is a factual subject. Lots of. Oh my God, he already answered. Chalo, others don't know, no? We will. What a preparation. What excellence. I see. Very good. Very good. That is the correct answer. Yes. Name an oxide of chlorine which is paramagnetic. She had not started halogens, she started asking questions. Without options only when I'm getting the answer, why should I give options? See, absolutely correct. Comment on chlorine's hybridization here. I've said oxide. So that's the reason the answer will be ClO2. Very good. One more new name, Satyam. So I know now. Wait 2 minutes, I'm taking rest. So I know now Satyam, Faizan, Vaidehi, Atika, Sapna, Palak, Ihina, Vaidehi Shri, Nandana, Chris, and many more. Good. Why is it paramagnetic? Paramagnetic substances are the ones which are actually weakly attracted by the magnetic field that your physics teacher will tell for our chemistry purpose. If the substance contains one or more unpaired electron, then this unpaired electron is alone. Just see its condition. Chlorine has 7 valence electrons. Chlorine has 7 valence electrons. One, two, three, 4, 5, 6, 7. This is alone in this hybrid orbital. unpaired electron. Got it, Nandana? Yes. Few more slides I've left. If I want to ask you people something, I will. Fine. Acha, chalo. Let me ask you one question. One more. Chlorine with cold dilute NaOH. Chlorine with hot concentrated NaOH. First one I'm expecting first. My God, my God, my God. See, I'm not here for balancing and all those things, so don't worry about those. The main products and side products also very good. What more to say? Everything you people are telling, that's very good, students. Before the exam, if I see you people are ready, prepared for anything, so many correct answers. None of the answers are incorrect. Here at least. Somewhere else, if you have done, that's different thing. Okay. The next family waiting for us. Let's complete P block today. Let's see if we can. Fluorine, chlorine, bromine, iodine, they're all four non-metals. Last one, these two basically, last two are radioactive basically. Tennessine, as I told, I remember its IUPAC name. That's easier. So, halogen family welcomes, we welcome halogen family. The first four are non-metals and the last two are radioactive in nature. Halogens mean salt forming. They're not going to ask these things in the exam. So we'll come to the main point. No doubt, bromine is a liquid, iodine is a solid which can sublime. Chlorine and fluorine are gases. Fluorine is basically a pale yellow gas. Everyone knows about greenish yellow chlorine, reddish brown bromine, and violet iodine. What is the reason for color in general? The unpaired electrons gets excited, and from the excited state, when they jump back to the ground state, they emit energy in the form of radiations, which apply in the current region. We can see the respective color. You know halogens exist as X2, F2, Cl2, Br2, I2. They don't show allotropy or catenation. And fluorine, students, do you know? I would like to know a little bit related with our electrochemistry. Always I link things with organic or physical. Becomes an interesting couple. So, students, in the entire periodic table, you will find that the value of standard reduction potential is maximum for fluorine, and hence fluorine is the correct no strongest strongest dash agent. What agent? Very good. Oxidizing agent. Students, if you are helping me with so much, something you had previously learnt in aqueous solution, which is the strongest reducing agent. Strongest reducing agent. If oxidizing agent, I'm helping you recollect, or you are helping me recollect. Okay, okay, that's true. So this anomalous behavior of always the first element of a particular group is due to its small size, high electronegativity, highest electronegativity here, 4.0 in the Pauling scale. Okay, so small size, high electronegativity, absence of d orbitals, non-availability of d orbitals. I don't understand low bond dissociation energy. Joking, I'm asking you people. So it's small size, highest electronegativity, absence of d orbital, and a very high positive reduction potential, which makes it the strongest oxidizing agent, makes its unique or its behavior different from rest. This point Small size, strong bonding. No, O2, O2, O and O was forming a strong double bond. N and N was forming a strong triple bond. I know F and F single bond, but they are small in size, 2p, 2p. Even the head-on overlap should be quite compatible. What's the problem? Why, if they are saying the bond association energy is less, we have to trust them? What's the problem, students? Why is it showing or written low bond association energy? Actually, for the halogens, the bond association energy value is experimentally determined chlorine, bromine, then comes fluorine and iodine. Iodine, we understand. Too bulky person, large, not only bulky, large atoms. So it's easier to break the bonds. Understood. What? Why does fluorine come so back? Like it was coming first in the class, now it came third. Why? Because electron pair, small size and high electron pair repulsions. Three lone pairs you are loading. You are loading three lone pairs in such a small fluorine. Okay, we are loading three lone pairs in such a small fluorine, and it's very small in size also. So this interelectronic repulsions are really very high, students. So small size, high interelectronic repulsions, the bond association energy is literally quite low as compared to the other halogens. Iodine, it has to be worst. It's just better than the worst. Like that it is. Yes. Size, everyone will agree. Ionization energy and size inversely related. Agreed. Electron affinity, there is an anomaly. Tell me, what's that? Which one will have the highest electron affinity, not only in this particular group, but in the entire periodic table? Chlorine. And you know the answer. Everyone knows, means in the group. That's what I can see in the chats. So chlorine here has the highest electron affinity because the small size fluorine is already struggling with so many valence electrons in that small space. The added electron will face a lot of repulsion, and hence the electron affinity of fluorine is less than that of chlorine. Good. Electronegativity, no doubt. Fluorine is the highest and it decreases regularly. Any anomalous behavior anywhere you found right now, not even right now, later on also, not only right now, later on also, let me know. Bond length, which depends upon size, but bond dissociation energy, fluorine goes back or much lower in the sequence because the very strong repulsion between the non-bonding electron pairs. Melting and boiling point increases regularly. Size increases, van der Waals forces are more energy is required to convert solid into liquid or liquid into gaseous state. Oxidation state, fluorine can show only zero or negative oxidation state. For other halogens, other than -1, you can see +1, +3, +7, +5 where? Say HClO, +1, +3, +5, +7. In some other oxides and oxyacids, you can also see +4 as well as +6 also, but less common, but you can still see. The oxides containing Cl, I'm sorry, the oxides containing +4 or +6 oxidation state have odd electron bonds and are usually paramagnetic in vapor phase. ClO2, oxidation number of chlorine +4, and yes, one thing we know which supports the line which is written here and is paramagnetic. These are the usual oxidation states except for fluorine, which exhibits only -1 because it's the most electronegative element. Oxidizing nature, no doubt, fluorine is the strongest oxidizing agent. Does it mean I2 can act as a good reducing agent? How reducing agent? It will be a weak oxidizing agent. Okay, just trying to confuse you, but again saw the time and thought no more time to Discuss these things after P block. If I discuss, well and good. Fluorine the most, iodine the least. Oxidizing. Strength of oxidizing agent. Students, the reactivity of halogens decreases down the group. One more thing. The halogens reactivity decreases down the group. So what happens is, say for example, I have NaF. Uh-huh. How can I have NaF? Suppose I have NaI. Just like displacement reactions, F2 being more reactive than I2 can replace I here. Just like displacement. F is more reactive than I. So NaF along with the liberation of I2 can be possible. But if it's the other way around, the less reactive can't replace the more reactive. I'm sorry, I know what I did. I2 cannot replace fluorine. Iodine can't replace fluorine. Fluorine can replace iodine. Got my point? Very important. Students, just one thing which I can remember, important. What about the reactivity of alkali metals down the group? Now, reactivity of halogens decreased down the group. But if I talk about the alkali metals, very good. Their ionization energy decreases. It's easier to remove their valence electron and hence reactivity of group 1 increases down the group. Very reactive elements, all these halogens here. Very good. All the answers are correct. They react with metals as well as non-metals. So sodium can react with chlorine to form NaCl. So chlorine can react with metals. Chlorine can also react with non-metals like sulfur to produce sulfuryl chloride. So either ways it's possible. As just now mentioned, the reactivity of halogens decrease down the group, while the reactivity of the alkali metals increase down the group. There was one question, just like that question or practice question, I don't know, but this was an old JE question, which I know. So I thought of discussing. Ionization energy decreases for alkali metal, so its reactivity increases. While for halogens, the reactivity decreases down the group. On the basis of the reduction potentials, you can justify. Super halogen. The super halogen is not mostly taken into account during organic reactions. No, we do it with either Cl or Br. But here, due to its weak Ff bond because of high interelectronic repulsions, it's a weak bond here, much weaker than chlorine and bromine. Because of its high oxidizing power, because of its high electronegativity, it's special, it's highly reactive, and it's called as a superman, super halogen. Students, comment as you go down the group. Comment on its acidic strength. Okay. Acidic strength increases because Hi is not at all compatible. The bond length is more. It's easier to break the bond. Acidic strength increases. Bond length increases. Thermal stability decreases. Reducing nature. Because we've discussed so many similar things, it shouldn't be. It should not be unusual. Let's see if anything is there which you don't know. Ha. I'll tell you which one. Boiling point. Comment on the boiling point. So bond length increases. Agreed. Thermal stability decreases. Reducing, you'll get more of hydrogen. So reducing nature increases thermal stability because they are no more compatible because of sufficient size difference. Acidic character also increases. Fine. Yes. No, that was not the case. HF because of hydrogen bonding, then HI due to its size, and then HBr, and then HCl. But in the case of melting point, it was observed that experimentally determined things. Here I can justify hydrogen bonding and remaining size. Done. It doesn't regularly increase or decrease. This is the reason where they issue. Very strong hydrogen bonding. It's difficult to break the bonds and convert it into the gaseous state. Strong hydrogen bonds. Now in melting point, it was experimentally observed that it's HI, then HF, then HBr and HCl, and we cannot do anything about that other than checking whether it's correct or not. Oh, due to hydrogen bonding, as I always say. Boiling point questions are more important here, huh? Im- Melting point, can't help. Hydrogen bonding makes its association strong, but HI is more than HF. Experimental setup determination, what to do? When it forms oxides, no, it can form various oxides. But fluorine can only form two types of oxides, O2, I'm sorry, OF2 and O2F2. Chlorine forms large number of oxides, iodine the least. I was thinking, students, what might be the reason? Iodine least. Iodine is quite large and oxygen second period element. So maybe not that compatible is what I was thinking. Okay, so chlorine, bromine, iodine. They form various types of oxides in different oxidation states, ranging from +1 to +7. OF2, O2F2, Cl2O, ClO2, Cl2O6, Cl2O7, drawing these structures, learning to draw mainly this oxides of chlorine structure is relevant. We just do ClO2, Br2O, BrO2, BrO3, I2O5. Mm, which one has greater bond angle? H2O or OF2? Very good. But a few more answers I want, not only one person. I'll not name anyone who has not given correct or incorrect answers. Like, okay. Now let's discuss. Both are sp3 hybridized, two bond pairs, two lone pairs. So you know oxygen is much more electronegative than hydrogen. So the bond pair of electrons are quite closer to oxygen. But here fluorine is more electronegative, so it's more towards fluorine. So this gap is less. This is okay compared to each other. So this gap being less, it will try to slightly move apart to minimize little repulsions here. So water will have the difficulty. I know it can't move more apart because the lone pairs are waiting to eat it. So, but slightly as compared to this case space is quite more because fluorine is more electronegative here. Oxygen being more electronegative here, the space is less. So it has to expand little more. So water more than Web2 is my answer. Would you people agree? I was thinking in this direction. Anyway, s- what would you like to say? I'll not say much now. We'll discuss only a little. And after our lunch break, we'll resume. Tell me, correct or incorrect? Do you have anything else? I thought in this way. Without checking the experimental value, I thought in this way. If the central atom is same, then what happens is bond angle will be more if the electronegativity of the side atoms is less. But I don't ask people to memorize any things or definition. What about the lone pair on fluorine? It will remain like that. It will be there. I've just not drawn. But I'm talking about the bond pair, OF bond pair, OF bond pairs, OH bond pairs. So here the bond pairs are quite close. So when they are quite close, they will face more bond pair repulsions. So here that they are quite comparatively, because there are two lone pairs, there are two lone pairs. So lone pair repulsion is same in the first case also, second case also. But here the bond pair repulsions being more in the first case, water should have greater bond angle than OF2. Fine. Yes, students. Interhalogen compounds. The halogens, chlorine the most, chlorine 3, 3 or 3.16, right? Fluorine 4, 3 or 3.16. Then bromine and iodine, the electronegativity value decreases. So amongst the halogens, there is sufficient electronegativity difference, sufficient enough for them to form covalent bonds. You don't need very high electronegativity difference so that they'll form ionic compounds, no? So when halogens combine with themselves, they'll form a lot of what compounds? Interhalogen compounds. Now you'll observe that you get IF7 but not ICL7, because what happens is when side atoms are too large and too many in number, steric repulsion or steric crowding will be there. Steric repulsion or steric crowding will be there. So what happens is BRF3 will be there. So that's the reason that ICL7 or IBR7 or IF5 or ICL. IF5 is still okay. IF5 is possible, students. IF5. F chalega. Okay. ICL5 or IBR3, BR3 also. BRCL3. They'll be comparatively less stable because these bulky groups will cause a lot of steric hindrance. Students, all of them are either solids or liquids except for CLF, which is a gas. So, if the side atoms like is small in size, a lot of compounds can be formed. Means if a lot of fluorides you will observe rather than chlorides or bromides or iodides. See, you heat them and you get the different interhalogen compounds. Hybridization of bromine in BRF5, iodine in ICL3. With that, we'll end up this class. We'll go for lunch and then we'll again come back 11, 1:45. Comment on this, these two questions. Hybridization, a BR and BRF5 first. SP3, D or D2? Ah, now it's correct, D2. 5 bond pair, 1 lone pair. Square Pyramidal. Here. Okay. Enough now. Now we should take a break and then continue with the remaining discussion. Fine.
Yes.
Thank you, everyone. After the second session, I'll upload everything.
Thank you, ma'am.
And maybe group
Okay.
16 at least I can upload now, no? Okay. Thank you, everyone. We'll meet right now. Just now. Bye bye.
Thank you, ma'am.
Thank
I'll
you.
end the meeting.